Part E is the last part of this section, and we'll be looking at special types of functions called even and odd functions. And the reason why that these even and odd functions are interesting and special are because they're going to remain invariant under certain reflections. So let's just go ahead and define them. So definition. We say that a function f of x is even if f composed with our negative x is actually going to be equal to f of x for all x in the domain. So geometrically, what an even function is it's a function that even if we reflect along the y-axis, nothing is going to change about it. So an example of an even function would be the quadratic y is equal to x squared. Reflecting this function along the y-axis just gives you the same function back. Okay, so let's go ahead and define an odd function. So we say that f of x is odd if we have that f composed with a negative x is equal to a negative f of x for all x in the domain. So let me just go ahead and label this graph even so we don't mix it up with our odd graph. Now the geometric interpretation of an odd graph is a little more complicated, but not too much more complicated. So what an odd graph is saying is that if first we reflect this graph across the y-axis, and then we reflect this graph across the x-axis, we get our original graph back. So an odd function is just a function that if you compose it with a horizontal and a vertical reflection, then you get your original graph back. Let's go ahead and do an example. So this is going to be example 5. And what we want to do is we want to determine if the following functions are even, odd, or neither. So our first function, we're going to have f of x is equal to x to the 5th plus x. And our second function, we have g of x is going to be equal to 1 minus x to the 4th. And in our last function, we have h of x is going to be equal to 2x minus x squared. So before we show the solution to this example, let me go back one page and just make a quick note. Notice in this definition that in both cases, we have f composed with a negative x here. And in one case, we have f of x, and in the other case, we have a negative f of x here. And what we can notice is that a function is either even or odd, but it's not both. So what does this remark tell us about this particular problem? It tells us the following, that if a function is even, then it's not odd. And this is going to be true in almost every case. And in the very same way, if a function is odd, then it's not going to be even. And the only exception, I believe, is going to be the constant function 0. So let's go ahead and look at part A. Let's go ahead and check to see if this function is even. So, well, we don't have to do that. Let's go ahead and just look at what happens of f composed with our negative x here. So this is going to become a negative x raised to the 5th plus a negative x here. But this is equal to a negative x raised to the 5th plus a negative x. We can pull the negative 1 out, and this is going to be a negative x to the 5th plus x here, which is equal to a negative f of x here. So this, in this case, f of x is odd. Moving on to part B. Let's compose our g with a negative x here. And so this is going to be equal to a 1 minus a negative x raised to the 4th. and this is equal to a 1 minus x raised to the fourth, which is equal to g of x. And this tells us that our function is even. So then in part C, again we compose our h with a negative x, and this transforms our function into a 2 composed with a negative x minus a negative x squared here. This is going to be equal to a negative 2x minus x squared. But this is not equal to a negative times 2x minus x squared, which would have been a negative h of x, and it's clearly also not equal to a 2x minus x squared. And so in this last example, h is neither even nor odd.